Okay, so you probably heard a little bit about the new Zen scheduler that we're trying to write here. So this is what I'm going to cover today. And my goals for this talk are fairly straightforward. First, I want you to be able to understand the problem. Why is it that we need a new scheduler? Then I want you to understand the idea of a reset event, how they work in Credit 1 and how it works in the new scheduler I'm developing, Credit 2. And I'm going to explain what all that means as we come to it. Finally, I want everyone here to know the design target and the plans for the future for the scheduler so that you can participate, ideally by writing code, but at least if you have something you want to change, some design target you want us to consider that we haven't considered, want you to be able to communicate that to me. So to accomplish those goals, this is what I'm going to talk about. I'm going to talk about issues with the current scheduler, the design target for the new scheduler. I'm going to talk about a little bit of theory, where I talked about this reset condition that I sort of discovered in the course of trying to develop new algorithms, and then some of the future work that we need to do for the scheduler. Okay, so what's wrong with the old one? The biggest thing that's wrong with the old one is the advent of this client virtualization. So as kind of an example, I set up a virtual machine to play audio through the host audio adapter. And the audio VM, when it was playing audio, if it was running all by itself on the empty system, the audio played fine, and it took about 5% of the CPU. Then I brought up two other virtual machines, both of them doing kernel builds, and so that each of the virtual machines were taking about 97% of one CPU. So this was a two-core system, so there's 3 virtual machines, so the fair share for the audio VM was 66%. So it should have plenty of CPU time to be able to process the audio. However, when I played the audio, competing with the 2 kernel build workloads, then I had about 30 to 40 skips in the audio listening over 5 minutes. So in a workload like audio, where 1 skip per hour might just be barely tolerable. So 30 to 40 skips over 5 minutes was just really, really unlistenable. And I also discovered in the course of this that the current scheduler, the credit scheduler, is not fair to latency-sensitive workloads. So for instance, if you set up network conditions such that an SCP, which is secure copy over SSH, from a machine off the box into a VM, if its fair share is 50%, it won't be able to use all 50% of its CPU time. It will only use 20 to 30% if there's competition. Whereas if there's no competition, it can typically use, if it's running on an empty box with no competition, it'll take about 70%. So it's not that it is not work to be done, it's that it's not able to use it effectively. Furthermore, as the number of cores are increasing quite a bit, I think there's probably already boxes that exist that have 4 sockets, each socket with 8 cores, each core with 2 threads. We have 64 schedulable entities. And it's not unreasonable that in the next couple of years we might reach 128. And so the load balancing with the Credit 1 is fairly unpredictable, and it's not scalable because it involves each core talking to every other core. So you have this n squared kind of explosion. And of course, there's other things that are coming up that people are interested in. Power management, hyperthreads are coming back. And so for all these reasons, we need to take another look at the scheduler and see what we can do with it. All right, so what are we aiming for? Whenever you go on a journey, it's always better to have an idea. It's always good to have an idea where you're going so that you know which direction to go and you know when you've gotten there. So ideally, I'd like to make one scheduler to be able to cover 3 main Zen use cases. The first is server consolidation. And the key challenge with that one will be effectively dealing with server VMs that have a large number of vCPUs. The second is virtual desktops. And the key challenge there will be dealing with a very large number of VMs that wake up and run for a short time and go back to sleep. And the final one, which I've mentioned already, is client virtualization, such as Zen Client. And the key challenge there will be latency-sensitive workloads like audio and video. So in each of these scenarios, we're going to evaluate the the scheduler by several criteria. The first is fairness, which is getting the amount of CPU that you promised. So if your fair share is 66% and you want to use, if you can use 66% of the CPU, then you get at least that much. The next is throughput. Ideally, given the fairness, we'd like to be able to maximize the throughput of the whole system. And one of the goals we want to look at is also graceful performance degradation. So as the amount that you would use on a empty system and your fair share goes down compared to that, we want the performance to drop, sort of gradually degrade, as opposed to hitting a cliff and then just falling off. The interface that I'm aiming for is very similar to the current interface. We'll have a weight, which will be how to divide the CPU when overcommitted, and a cap. A lot of people have requested the maximum amount of CPU that any given VM can have. Another thing I want to add is a reservation, which would be a minimum percentage of the CPU. So that you could say, this VM, it has a weight of whatever, but I want it to always have a minimum of 10 or 20% of the CPU if it wants it, regardless of the weight of the other VMs. Okay, so in the course of trying to develop a new credit algorithm, I kind of developed that. I found out that there was sort of an equivalence class of algorithms. Any scheduling algorithm which has one value per CPU, this could be credits, this could be time, if you're familiar with the borrowed virtual time scheduler, debits, or anything like that. There's one single scalar value, okay? And if this value is modified based on the amount of time that it's been running, wall clock time, time block time on the run queue, and so on, then almost all of these algorithms are actually isomorphisms of each other. You can map this algorithm onto this algorithm, and they have the same basic properties when you actually run. And one of the key problems that all of these have to solve is how to deal with vCPUs that don't use all of their allotted time. So in many cases, you'll have virtual CPUs that don't use all of the time. And if you say have for the credit scheduler, if you're just adding credits on a regular basis, well, some will, they'll be given credits, and they'll burn some of the credits, but not all of them. They'll be giving credits, and some of the credits, not all of them. So their credit will just keep kind of going up. Whereas other ones will be given some credits, and because they're burning as much as they possibly can, they burn more than their fair share because the other ones aren't using it. So they tend to go down and down and down. So there's a tendency towards divergence. So to deal with divergence, I explored a lot of different alternatives, including guessing how much credit might be used, trying to make everything zero sum, so you're only putting into the system as much credit as you might know might be burned, and so on. But the best solution that I found, and the ones which both the credit and the borrowed virtual time scheduler use, is what's called a reset event. A reset event discards unused credits and tends to converge vCPUs that have gotten too far behind. Okay, so credit one has many different issues. It has a very long time slice, so a CPU burner can run for a full 10 milliseconds without being interrupted. Actually, sorry, 30 milliseconds. I can run for a full 30 milliseconds without being interrupted. It's sorting by priority rather than by credit, and then within each priority, it's scheduled to round robin. And if anyone knows any theory from operating system class, round robin is unfair to scheduled entities that yield compared to ones that just use up their full time slice. There used to be a thing with probabilistic debiting that has since been fixed because of a vulnerability to cycle stealing that the Amazon guys found. But the key issue with credit one is how it deals with the reset condition. So let me describe the credit one algorithm, how it actually worked. It basically assumed that all virtual machines fell into two categories. CPU burners, which burn as much CPU as they could, or IO-bound VMs, which burned almost no CPU at all. Therefore, it categorized all virtual CPUs into one of two categories, active and inactive. So active VMs, credit is divided every 30 milliseconds according to weight. And conceptually, they burn credits at a fixed rate. There's two priorities, under and over. If you have positive credit, you're in the under priority. If you have a negative credit, you're in the over priority. And then scheduling within each priority is round robin. Now, for the non-active VMs, they do not earn credits, nor do they burn credits. And essentially, if you look at the mechanics of the thing, they almost always run at another priority called boost priority. And the transition between them works like this. To move from active to inactive, if a VM ever earns a full 30 milliseconds worth of credit, then it's transferred, then the credits are all thrown away, set to 0, and it becomes inactive. And fairly soon after that, it usually will be boosted because it's just yielded. To go from inactive to active happens when a virtual CPU is interrupted by a timer tick. Now, the problem is that inactive is a very unstable place to be. So you're guaranteed to be hit by a tick eventually. So for instance, I mentioned the audio VM took about 55% of the CPU. That means that for any given tick, there's a 5% chance that tick is going to hit the audio VM. So we'd expect about 1 in 20 ticks to hit the VM. And so since ticks happen every 10 milliseconds, then we can expect, on average, the audio VM to only spend 200 milliseconds in boost before going back to being marked active. And the problem then is that when you're marked active, you start with 0 credits, and then you're debited credits. So now you're in the over state. You're scheduled behind every other VM in the system, which is in under, or boost. And you have to slowly dig your way out, earning credits, until you get to 30 milliseconds again. And then your credit will be reset back to 0, and you'll be marked active, just to do the whole thing again. So any vCPU which uses less than its fair share, no matter what percentage that is, will flip back and forth between active and inactive. And every time it flips from inactive to active, it's basically at the very, very last place in the run queue. So for credit 2, the reset condition is core to the algorithm, making the reset condition work in the way that I think is effective. So the basic description works like this. The credits for all VMs start, we'll start simplified and I'll make it a little bit more subtle. The credits for all VMs start at a fixed value. Credit is consumed at different rates based on the weight. So if you have a higher weight, then you consume credits faster, because you'll go down faster. And if you have a higher weight, you'll consume credits slower. If you have a lower weight, you can consume credits faster. And you're inserted into the run queue based on how many credits you have. And the reset condition works like this. When the credits of the vCPU at the front of the run queue are less than or equal to 0, then you set everyone's credits back to the starting value. And I should point out here that no run queue sorting is required here, because you can just leave the order all the same, because everyone should be equal. And as a slight refinement, instead of just setting everyone's credits to a fixed value, what I actually do is I clip it down to a low number and then add a fixed value. Okay, so this is kind of a graph that gives you an idea how the algorithm works. This is actually, it's not a trace of an actual run, but it's a graph from a simulator that I developed to be able to quickly iterate over the algorithms. So on the x-axis we have time, and on the y-axis we have amount of credits left. And each color is a different virtual machine. So when it's flat, that means it's not running, either because it's blocked or because it's waiting for the CPU. And when there's a slope, that means it is running. Okay, and so you can see some of the ones have a steeper slope than the other ones because they have a lower credit or a higher credit. And most of the VMs, they run at all different times, but most of the VMs are consuming all of their CPUs. And you can see that each VM will kind of go out until it's the one with the highest credits, and then we'll run for a time until it's kind of behind, and then it will block until it's one of the highest credits again. And the blue line represents the audio VM. So it wakes up, it runs for a very short time, and then it goes back to sleep. And as you can see, it basically always gets to run exactly when it wants to, because it always has more credits than everybody else. And in the middle here, we have the reset condition. So when all of the VMs have gone down to slightly negative, and so the VM at the front of the run queue, when it's going to run something, is negative. Then we reset everybody's, we clip everybody's credits and reset it back up. And so you can see that the audio VM starts at the head of the run queue already, because when we did the reset, it had a huge number of credits left. So it doesn't keep all of those credits, but it does keep some of them in the next iteration. Okay, so the other major change that I just want to throw out there is that rather than having one run queue per schedulable entity, per thread or per core as we had before, I'm experimenting with the idea of having one run queue per L2. So the main reason to avoid quick migration between processors historically has been for cache effects, right? But in modern processors, threads and cores, and a small number of cores, typically share an L2. And I'm sort of told, I haven't been experimented with it, the L1 caches are generally small enough that if you do a context switch at all, then it's not really worth, you've blown your L1 cache and it's not really worth worrying about after you switch back to it. So the L2 caches are the only thing that we care about. And by having one run queue per L2, we get instant, perfectly fair load balancing across the cores and threads shared by that one L2. And that also means that for most single socket boxes, you don't need to do any fancy load balancing algorithm because there is only one L2 in, like, say, a laptop or a small desktop system. So things will automatically be bounced across them there very fairly without having to do anything fancy. Okay, so the early results, audio is better with the same setup as before. There weren't any skips. That's not surprising. And the network is more fair. Doing an SCP off the box has been able to get a full 50% of its CPU share. Now, the status right now is that the credit scheduler has been checked into unstable. It's been checked in since shortly after the 4.0 release. It is not the default scheduler, so you have to switch it to the scheduler. It still needs a lot of work. For one thing, it doesn't actually have any of the design for the multiple sockets yet. So it has the infrastructure in there to make it so you can have several run queues. But right now, there's only one run queue. So no matter how many sockets you have, no matter how many big things, there's one big gigantic run queue. So that's going to run fairly poorly on a multiple socket system. But if you have a single socket with a single L2, it should work not too badly. And what I'm working on the moment is setting up a test infrastructure to so that I can test all kinds of different combinations of workloads and make sure that we cover all the different combinations and make sure they work really well. And so that as I'm developing it, we have kind of a regression test. And if someone else comes in and says, hey, my workload didn't work very well, here's a patch that makes my workload run better, we can run that through our regression testing system and say, but it makes your workload run better, but it makes this other workload run worse. How can we try and make everybody run about as happy? So yes, as I said, future work, we need to work on load balancing. And as I said, the load balancing only needs to happen between L2 run queues. My idea was that we should have explicit load balancing based on historical load. So look at the load that each run queue has, and then try and balance based on that. Yeah, ideas for hyperthreading, power management, and NUMA. Okay, so I've talked about issues with the current scheduler. I talked about the design target we want for the new scheduler. I talked about the reset condition, how that fails to work in Credit 1, and how hopefully it works better in Credit 2, and some of the future work. So I think with that, okay, hopefully, now you understand why we need a new scheduler. Hopefully you understand reset events, and you have an idea where we're going with things so that you can participate in the process. And with that, I'll take any questions.
George, Suzanne?
Yeah.
Okay. Let's see. I'm the kind of guy who has never really messed much with schedulers and never changed a scheduler or set a parameter. And I suspect that's probably representative of most of the people in the room. In working for my presentation for tomorrow, I was running a workload and I discovered a case, I don't know whether it's a bug or an anomaly or what, where the credit 2 scheduler was substantially a few percent worse than the credit 1 scheduler.
Yeah.
And I know you touched on this a few minutes ago, but could you comment on that? Should everybody in the room be trying both on their workloads and trying to feed that information back to you so we ensure that it is indeed going to be better before we switch it as the default?
Yeah, I think, so in your case, I definitely want to try and duplicate results and put those results into the testing system. And definitely one of my goals for the scheduler is that the performance on like a bare system should be no worse than 1% slower than the current credit 1. So, and hopefully, I mean, it'll be even less than that. So, yeah, so I mean, test it. If you find anything that's a really big, obvious problem or obvious really unfairness, let me know about it, and I will do my best to put that into the testing system and try and figure out what's going on.
Okay, any other questions?
That's right behind you.
So do you have any plans for us, any kind of priority classes such as pseudo real-time priority of any form?
No, I mean, at this point, my hope is that we should be able to make it so that everybody can kind of live together and latency-sensitive applications can run, with short latency, and CPU-intensive applications should be able to have, big chunks of the CPU time, and we have some kind of balance of those things. If it turns out that we can't accommodate everybody with the CPU, then with this scheduler, then I think it might make sense to have a real-time specific scheduler. But I'm hoping that if your system is not overloaded, then everybody should be able to get the CPU when they need to get it.